Application ICs. IC voltage regulators LM78XX, LM79XX, fixed and adjustable 3-terminal regulators. A voltage regulator is a circuit that supplies a constant voltage regardless of changes in load currents. IC voltage regulators are versatile and relatively inexpensive. IC voltage regulators features programmable output, current voltage boosting, internal short circuit current limiting, and thermal shutdown. IC voltage regulators are of the following types: fixed output voltage regulators, positive and or negative output voltage; adjustable output voltage regulators, positive or negative output voltage; switching regulators, and special regulators. Most practical regulators are of linear type. The impedance of a linear regulator's active element may be continuously varied to supply a desired current to the load. Switching regulator, a switch is turned on and off at a rate such that the regulator delivers the desired average current in periodic pulses to the load. Fixed voltage regulators, positive voltage regulator. The 7800 series consists of 3-terminal positive voltage regulators with 7 voltage options. Device type, voltage output, maximum input voltage. So we have 7805 output voltage is 5 volt, 7806 output voltage is going to be 6 volt, 7808 8 volt, 7812 12 volt, 7815 15 volt, 7818 18 volt. For these regulators, maximum input voltage is 35 volts. And finally we have 7824 whose output voltage is 24 volts. The last two digits represent the output voltage, for which maximum input voltage is going to be 40 volt. These ICs are designed as fixed voltage regulators with adequate heat sinking. So this is the configuration. So it's a 3-terminal voltage regulator, and terminal 2 is the common or ground terminal. Between 1 and 2 we give the input, and between 3 and 2 we take the output. These ICs also have internal thermal overload protection and internal short circuit current limiting. The difference between input and output voltages Vin minus V0 is called a dropout voltage, typically 2 volt. C0 is used to improve the transient response of the regulator. The internal circuit diagram of a 3-terminal positive voltage regulator is something like this. So it is having a lot of transistors, Zener diode, and resistors. Also a complex circuit. The functional blocks of the regulator circuit are transistor Q10 along with resistance R9 forms an emitter follower which provides best drive for the series pass output stage. Transistor Q11 with the multiple collector terminals provide a multiple current source configuration. Transistors Q12 and Q13 with the Zener diode D1, R11 and R12 provide thermal shutdown. Typical performance parameters: line regulation, load regulation, temperature stability, and ripple rejection. Line or input regulation, change in output voltage for a change in the input voltage. Load regulation, change in output voltage for a change in load current. Temperature stability or average temperature coefficient of output voltage, which is nothing but the change in output voltage per unit change in temperature, normally expressed in millivolts per degree centigrade. Ripple rejection, the measure of a regulator's ability to reject ripple voltages. Next we have adjustable voltage regulators. So they provide output from 1.2 volts up to 57 volt. Reliability advantages. Improved system performance by having line and load regulation of a factor of 10 or better. Improved overload protection, allows greater output current over operating temperature range. Improved system reliability with each device being subjected to 100% thermal limit burn-in. The LM317 series is the most commonly used general purpose adjustable voltage regulators. So we have adjustable positive voltage regulator, LM311 series adjustable 3-terminal positive voltage regulator. Here we get the output voltage from 1.2 volt to 57 volt, whereas output current from 0.1 ampere to 1.5 ampere. Typical connection diagram for the LM371 regulator requires only two external resistors to set the output voltage. Reference voltage V reference between the output and the adjustment terminal. V reference voltage is impressed across resistor R1, and since the voltage is constant, the current I1 is also constant for a given value of R1. Because resistor R1 sets current R1, it is called the current set or program resistor. In addition to the current I1, the current I adjust from the adjustment terminal also flows through the output set resistor R2. I adj is very small and constant with the line and load changes. Output voltage V0 is V0 equal to R1 I1 plus R2 into I1 plus I edge, where I1 equal to V reference divided by R1. R1 is the current I1 set resistor, R2 output V0 set resistor, I edge adjustment pin current. Substituting the value of I1 and rearranging, we get V0 equal to V reference by R1 plus R2 into V reference by R1 plus I edge. V0 equal to R1 getting cancelled, V reference plus R2 V reference divided by R1 plus R2 I edge. V0 equal to V reference plus R2 V reference by R1 plus R2 I edge. So you take the common first two terms common parameter V reference. So V0 equal to V reference into 1 plus R2 by R1 plus I edge into R2, where V reference voltage between the output and adjustment terminals. However, the current I edge is very small and constant. Therefore, the voltage drop across R2 due to I edge is also very small and can be neglected. So V0 can be written as V0 equal to 1.25 into 1 plus R2 by R1. Output voltage V0 is a function of R2 and can be varied by adjusting the value of R2. When external capacitors are used with LM317 C2 to improve transient response, C3 to obtain very high ripple rejection ratio. It is necessary to add protection diodes to prevent the capacitors from discharging through low current points into the internal regulator. Block diagram of LM317 is shown in this diagram.